Hi everyone, welcome to the Magical Mystery Tour. This is going to be a roundup of some observability databases and a little bit of a comparison to Postgres, which maybe isn't quite an observability database, but we'll get into that. So first of all, I just want to thank you for being here and for caring about this. This is a quote that I heard from Patrick McFadden in his talk at ApacheCon in Minneapolis. Developer will never ask you, hey, what file system is that? So you're the special few who actually do care about this kind of stuff. And we're going to get down into like the nitty gritty a little bit of how some of these databases work and how that can inform why we might choose one or another. So quick introduction, I am Josh Lee. I am an open source advocate at Altinity. We do hosting and support for ClickHouse. My specific expertise is with ClickHouse, Kubernetes, and OpenTelemetry. And importantly, we are not affiliated with or associated with ClickHouse Incorporated. We're just humble open source contributors. So quick definition, right? Observability, it's a buzzword. So just want to give my definition. It's very, very simple. It's visibility plus understanding. Can we see what's happening inside the system? And do we have enough information about what we're seeing to understand it? Now, that's a simple definition, but it actually comes at a pretty huge cost. So this is just a rough rule of thumb. It's going to vary based on the shape of the actual application that you're building and the problems that you're solving. But as a rule of thumb, I like to say that you're going to have about 50 times more observability data than actual system data. That's just a huge amount of volume that we have to deal with, and it means that we need to develop specialized solutions so that we can actually deal with this and sort through this and get to the understanding in all of that visibility. So what are we storing? This will look familiar if you've seen me talk before, but real quick review. Of course, the signals themselves, right? That's the metrics, traces, logs, profiles, and events, all of the awesome signals that we have in OpenTelemetry. It's going to be the labels and tags, or as it's called in OpenTelemetry, right, the resource metadata, which is actually the really interesting information about the containers, VMs, and so on, processes, services that we actually care about, right? We care about those things as developers much more than we care about individual metrics, traces, or logs, or even really tags, right? And then from those things, we can build graphs and topologies, right? And graphs and topologies are expensive, so we might want to make snapshots to sort of keep track of what the graph looked like at a certain point of time. If we've got snapshots, we'll probably have deltas, and then we'll have some configuration, which doesn't really fit the analytics use case. It can go really anywhere. But what do we need for this, right? Well, first of all, we need writes that just never stop, right? In a worst case scenario, if your observability backend stops accepting data, it can actually crash your production app. Hopefully you've architected in such a way that that won't happen and you'll just drop data. That's a much preferable option. But even then, right, you're losing visibility and you're losing the ability to understand other problems, like why you're dropping data. So we need an observability database that can accept huge amounts of data very, very quickly without ever slowing down. Once we've got all of that huge amount of data, we need a very efficient way to compress and store it all. Observability data tends to be oriented around time, so we need time-oriented management and retention policies and TTLs and things like that. And we need real-time analytics. Now, this is another buzzword. It's one that I kind of don't love, but it is really, really useful, right? And it's not actual literal real-time. It's real enough time, right? It's real time to the humans that are using it. So on the order of seconds instead of minutes or hours. And when we talk about analytics, I love this quote from Peter Marshall that imply anything you can do with a group by statement, that's what analytics is, right? So really, when we talk about real-time analytics, what we're actually talking about is being able to do aggregations over rows across arbitrary dimensions very, very fast. We also often need full text search, especially when we're dealing with logs. If we're being organized about our resource metadata and our other metadata and tags and labels, then tag and label indexing and search can be really useful. We need to be able to read the last data point often. This is especially useful for alerting, where we want to see if the last data point falls outside of an acceptable range, and then maybe start an alert if it does. And updates, not so much. We don't really need those, right? Observability data tends to be kind of immutable. Once we write it, we don't need to change it. We're going to read it a bunch of times, hopefully, and then eventually delete it. So we don't need to optimize our database for updates. And when we do that, we can actually do a lot of things to make our database faster for all of these other use cases. So I wanted to kind of break this talk down based on these database archetypes, but it's actually a little bit tricky too. So instead, we'll quickly go through the archetypes. Then I'm going to actually talk about some of the tricks that the databases use under the hood and how they combine them all. But first of all, the archetypes, right? So we have OLTP, which is a online transaction processing database. This is a traditional database that we've all worked with, MySQL, Postgres, etc. So this is the most common database, and this is what you want to use if you need things like transactional guarantees, if you're doing things like actual money transactions or orders or things like that, where you need atomicity and consistency. Then we have OLAP, or online analytics processing databases. These databases give up some of those transactional guarantees in the name of speed and being able to really, really quickly read and aggregate across different dimensions. Time series database is sort of a unique type of database specifically built for storing metrics in observability use cases and also in other time series metrics type use cases. And then we have what I'm going to call sort of the search and analytics category of databases, which are typically used especially for logs use cases when it comes to observability. So getting into the specific databases that we'll be talking about, we have Postgres, which is a useful starting point because we're all familiar with it, and we can compare how it does things to the other databases. We have Cassandra, which is our introduction to the Lucene family of databases. OpenSearch is another Lucene database that's very popular for any kind of semantic search and also for observability logging. Prometheus is sort of our de facto standard for time series, and so we're going to look at the architecture of how it works and how time series data is typically oriented. And then finally, we'll look at ClickHouse, and then I have a few surprises at the very end. So, like I said, it's kind of hard to put these databases strictly into one category or another, because what's been happening over the last 5, 10, 15 years is that all of these databases have been borrowing tricks from each other. And so what one database was exclusively good at years ago, now they kind of all have at least some basic implementation of in some way. And you can really bend any of these databases to your will if you try hard enough. But they still do have their specialties. And so I've tried to put them on a spectrum here between OLTP, transactional databases, of which Postgres would be the most canonical example, ClickHouse being the most canonical OLAP, and then OpenSearch or Elasticsearch sort of being the canonical vector search databases, with everything else falling somewhere in the middle. So when we're talking about databases, one of the biggest bottlenecks, in fact, the biggest bottleneck, is actually getting the data onto and off of the disk. This is always going to be the slowest part of the database, no matter how fast our SSDs and NVMEs get. It just always will be. And so if we can minimize the amount of data that we need to read or write or update, then we can dramatically speed up our databases. So let's talk about how the different databases actually store the data on disk and how that impacts their operations. So at a high level, we kind of have these different strategies for storing data. We can store heap pages, which is just sort of trying to keep the database in a compact section of the disk and fill empty spaces with new data. We can use a commit log for additional durability so that any data that hasn't specifically been processed to the correct place on the disk can sort of be replayed from the commit log. We have time series blocks, which are an append-only structure. And then we have immutable parts or segments, which is a way of storing data very, very quickly and then optimizing it in the background. So like I said, heap pages, right? It's sort of like a JPOD. It's just we've got some space that we want to fill up, and we have pages that get stored in this space. And each of these pages in Postgres, these are rows, but it can vary, right? There are some databases that would store documents instead of rows here. And say we want to delete some data, we mark a page for deletion. There's a vacuum process that is happening periodically that will remove any pages that were marked for deletion. And then the next time there's some new data, it gets inserted into the first empty spot so that we keep our data nice and compact. Then we have time series database blocks, right? These, as I mentioned, are append only. So we have one file for each time series, and when we get a new sample, we just append that data to the end of the file, which is really nice. Then we have immutable parts or segments with background compaction. So here what we have is we're basically using a batch insert to create a part or a block that has many, many rows in it. And then that gets written to disk. And then in order to make future queries faster, those parts are slowly ordered and merged into larger and larger parts based on an ordering key. And that allows us to then read the data even faster as that data gets compacted into larger parts. So to actually write the data, there are a few more steps, right? So as I mentioned, some databases use what's called a commit log or a write-ahead log. There are a lot of different names for this, but they're all basically the same idea. And it's that you are essentially writing a log of all of the inserts durably to the disk, right? And that way, if the server reboots before some of that data actually gets organized into the specific file format of the database, you can replay those queries and recreate those writes. If we have multiple processes reading and writing from the database at the same time, we need some way of managing the concurrency and sort of giving those processes a consistent view of the world, at least for each process, right? So there are a few different strategies that we can use for that. We have multi-view concurrency control and vacuuming, which I'll talk about. We have tombstone deleting, which is really just a way of marking specific files as deleted, and then they will be ignored by future reads. And then we have last write wins, where you essentially just keep writing data, and whichever write had the latest timestamp is the one that will be used in queries. Then we need to actually keep track of where we put the data. So in Postgres, the way that this works is with a balance tree index, right? Balance tree would be really expensive if we were storing all of our data in it, because we're moving it around all the time. But if we have the data in those nice heap pages, those heap pages, then we can keep track of which pages contain which data using a balance tree index. So combining all of those things, right, we can build a Postgres. We have a write-ahead log, heap pages with multi-view concurrency control, and then balance tree indexes. What this gives us is a database that's really well optimized for updates, upserts, and row-level reads. It gives us all of the strong ACID guarantees that we need for things like financial transactions, but it does mean that scaling horizontally and adding replication can be a bit challenging and requires some strategization. So let's talk about something a little bit faster and a little bit more purpose-built for observability, and that's an analytics and a search architecture. And sort of the first implementation of this, or one of the first implementations of this type of architecture, is log structured merge tree, which is used in Kafka, and it's also used in the Lucene engine, which is used by a number of databases that we're going to be talking about. This is a great diagram of how log structured merge tree from Ben Stopford. I highly recommend reading his blog. He explains the stuff way better than I could. But basically what we have is we have these key value pairs that are buffered and stored in memory, and then periodically flushed to disk is small sorted files. And then just like we were talking about with the background compaction, right, those files then get merged into larger and larger files that can be read more efficiently. And that is what powers, as I said, the Lucene family, which includes Cassandra, Elastic and OpenSearch, and Apache Solr, among a number of other databases. It's also used inside some proprietary observability tools. You've probably written a Lucene query, even if you didn't realize you were writing a Lucene query. It's just this format. So if you're used to like log search tools in a lot of observability tools, or if you've used OpenSearch or Elasticsearch, then you've written a Lucene query. Cassandra is a great example of a document-oriented Lucene engine-powered database. So it basically is like Postgres in that it is no LTP, but it is optimized for the really rapid ingest that we said we needed for observability, especially for logging. And it could be used for that. There are still some efficiency issues, but it can work. Cassandra actually uses CQL, not SQL. It's a derivation of SQL, not the Lucene query language. So vector engines then take that log structured merge tree and add some really, really intelligent indexing on top of this. And that is what allows us to do things like semantic search and full text search. So for full text search, we need something like an inverted index. So if the typical index stores a primary, stores the location of specific primary keys, an inverted index flips that, and we have the actual data pointing to the primary keys rather than the primary keys pointing to the data. And so here, for example, any document containing the word cat would be pointed to by this inverted index with cat in it. This allows us, right, if we're thinking about literal search, this would allow us to really, really quickly find any document with a specific literal word in it, which is great, especially for logs when we know exactly what we're looking for. We can also speed these up even further and make them a little bit more optimized at the cost of some additional processing using what's called a Bloom filter. So a Bloom filter hashes the content of the data, and then depending on how we actually do that hashing, we can determine whether a specific sequence of words appears in the document anywhere. Now, we don't know for sure if it does appear, but we do know for sure when it doesn't appear. So there are no false negatives, and this allows us to very, very quickly skip entire sections of data, which if they're stored on disk and we don't have to scan that section of the disk, that's a huge win. But that's all just literal search. If we actually want semantic search, then we need to sort of upgrade our data type from strings to vectors. And vectors can be related to each other, right, in a multidimensional space. And in that multidimensional space, we can then group them based around their nearest neighbors. We can create hierarchies of these groupings so that we can quickly navigate to the area that so that we can, store sub-indexes and quickly find the sub-index that might contain the data that we're looking for. So this is a strategy called approximate nearest neighbor with a hierarchical structured world of multi-layered graphs. And it's how semantic search in something like OpenSearch or Elasticsearch works. Then we have time series databases, right? These are for our metrics. Prometheus is the de facto standard for metrics, and its implementation is pretty good. There are also a lot of Prometheus compatible alternative databases like Mimir and Danos and Victoria Metrics, right? The PromQL ecosystem is huge. The way that these databases work is we simply append that last sample. This is really, really great for drawing charts because we can just quickly scan the sections of the file that we care about, and also for alerting because we have that last sample, so we can just quickly read the last few bytes of every file and quickly know if we need to fire an alert. However, there is a challenge with the way that time series databases store these data. There's one file per time series, and if we look at how the dimensions and cardinality of those dimensions actually maps out, this is sort of a rough rule of thumb that your number of time series is going to be your cardinality to the power of the number of dimensions that you have. So that can create a cardinality explosion, which if you're running on open source Prometheus is probably going to knock it over. And if you're running on something like Datadog is going to absolutely explode your bill. So you want to avoid this when you're dealing with time series databases that do deal with cardinality in this way. However, one really nice thing about these time series databases and something that they share with column-oriented databases is that the data is all just laid out in a single section of the disk when we're looking at a single time series, which means that we can read it and do math and averages and things like that with it very, very quickly. So if we look at how this data is stored, right, in a typical row-oriented database, we're storing tuples that contain different values for each column in a specific row. And since those values are different types, right? So we can't really compress the data. And if we want to read a specific column, we have to read every single row, even if we're only looking at one specific column. Whereas in a column-oriented database, if we want to read a specific column, we can just read it. And because all of the data in a single column is going to be the same type, it means that we can compress it much better, and we can do things like delta encoding and use other strategic tricks to reduce the size of that data and scan it even more quickly. What this leads to is something that looks like this, right? So if we have a 59 gigabyte table with 109 columns, and we're using a row-oriented database and we want to analyze 3 of those columns, we have to read the whole database. In a column-oriented database, we're down to 3% of the database that we have to read. So 1.7 out of 59 gigabytes. If we look at those columns as compressed files, we read even less data. So we actually read less than 0.5%. And then if we split that work over 8 threads, which we can do, we get less than 0.01% to read the entire 59 gigabyte table. So this is sort of the power of column-oriented databases, especially when it comes to real-time analytics. ClickHouse as a database combines this column-oriented storage format with merge tree, which is its specific implementation of that background compaction process that we were looking at earlier with log-structured merge tree. The main difference between merge tree and log-structured merge tree is that merge tree is storing columns. So we have individual columns in each part, and then those parts are merged and ordered into fully merged parts, again, giving us increased query efficiency. Another trick that ClickHouse has up its sleeve is sparse indexes. So unlike inverted indexes and Bloom filter indexes, which actually contain a lot of data relative to the data that's being indexed, a sparse index has some pointers to some very large partitions of the data and just kind of says, based on an ordered key, hey, this data contains stuff between this and this value. We can also use what are called skip indexes, which are sort of an evolution on this, where we'd be maybe calculating the min-max of a specific column and using that to quickly identify whether a specific partition or granule is one that we care about. Okay, so that was a lot about the architecture of the databases. I did promise that we talk a little bit about how to choose a database. So this is a diagram that I use a lot, and as a starting point, these are great choices, right? This is actually something that I'm running in my home lab, and that's why this diagram has these specific things on it. But they're by no means the only things that you can choose, right? But in this case, I'm using ClickHouse for storing traces, Prometheus for my time series metrics, and OpenSearch for logs. Victoria metrics is something that we actually use at Altinity as part of our cloud as our time series database, because it sort of combines that time series oriented format of Prometheus with some of the background compaction tricks that we see in something like ClickHouse merge tree or a log structured merge tree. And so that makes it much more efficient than Prometheus in terms of both storage and compute. And so that's a great choice if you care about specifically time series databases. Loki is a great tool from Grafana. It uses actually a very similar structure and architecture to Prometheus in that it's just appending logs to the end of a file. It does not have inverted indexes and full text search. So if you want to do full text search with it, you do have to scan all of the logs, but it does maintain label indexes. So if you're organized about your labeling, Loki can be a really great and uncomplicated tool for storing your logs. And it's also something that we use in Altinity.cloud. And there are a ton of databases that I didn't have time to talk about. So just some quick honorable mentions: Vortex, Thanos, Lemire, TimescaleDB, which is an extension for Postgres, Apache Solr, Apache Druid, right? These are all great choices for specific use cases, and they have their advantages. Definitely check them out. So, okay, I'm a huge fan of just using what you have. And if you're at very small scale and you already have a Postgres database and you have some additional data that you need to throw somewhere, you could just throw it in Postgres or use one of the extensions that makes it adapted for things like time series data, right? And that is not a terrible choice, especially at small scale. I'm a huge fan of fewer moving parts. If you're absolutely hooked on full text search and you need it for finding all of your logs, then OpenSearch has your back. It's definitely going to be your best choice. If you just want to use one database for everything, this is sort of the topic of the talk that I gave at Open Source Observability Day last year, but I think ClickHouse is a pretty cool choice that can give you SQL-powered observability for all of your signals. That's kind of cool. If you're really specializing in wide event analytics, so looking at trace dimensionality or just actual wide events, then ClickHouse is awesome. It's a great choice. If you need to do a lot of full text filtering heavily before analyzing data, then OpenSearch can be a really good choice because, again, it can limit the amount of data that you actually need to scan when you're doing that analysis. And if you need to do alerting or anything where you need a lot of the last sample reads really fast, then you probably want a time series database like Prometheus or Victoria Metrics. And just as one final thing that's not strictly observability, but if you wanted to, for example, combine your observability data with business insights transactional data, you could use something like Cassandra, which gives you some of those transactional guarantees, as well as some of those OLAP-like speed qualities. Or you could just use something like Postgres, which is purpose-built for transactions and a great choice there, and probably something you're already using. And if your analytics is going too slow, you can use a connector, dump all of that data into something like ClickHouse or Druid or any other OLAP and do your analysis there. Here's a quick table of sort of all of the databases that we talked about and some of their attributes. Importantly, OpenSearch and ClickHouse, I think, mostly support many of the same types of indexes. It's just to varying degrees of maturity. So ClickHouse sort of started with the more analytics-focused indexes and has added some of the more full-text focused ones, whereas OpenSearch has been working in the other direction. But both can do both in a pinch. Prometheus and its cousin Loki, great for simplicity, right? And then Postgres and Cassandra are great for if you actually do need OLTP. That's all I've got. So thank you so much and happy querying.